Welcome to your second week of our Properties of Water unit. Today's discussion centers around what those properties actually are. So let's go ahead and get started. By the time we finish our PowerPoint, we should be able to answer these two questions. What are the physical and chemical properties of water, and why is water so important for our planet? This first slide covers just some generalizations about water. The presence of water on Earth is what makes Earth so special. In all of the planets of our solar system, Earth is the only one with enough water on it to sustain life. Water is odorless, it's tasteless, it's transparent, which means that we can see through it. And when you have enough of it, it takes on that blue color. And of course, we all know that without water, life cannot exist, and that is for animals and plants alike. These terms should look familiar to you. They are the main vocabulary that goes with this unit, and we will be covering them in this PowerPoint, starting with the polar molecule, hydrogen bonding, solubility, that's the whole water as a universal solvent. We'll be looking at surface tension, states of matter we're not spending that much time on because that was the PowerPoint from last week. We'll be looking at that freezing and melting point. We'll go over density and why water and water's density is different from other liquids. And then lastly, we'll be covering that specific heat capacity. This slide offers a really cool video by the Amoeba sisters. Yes, it talks about polar molecules, but it also talks about a lot of the other properties of water as well. I'm not going to play that for you on the voiceover. You wouldn't be able to hear it even if I did. So make sure that if you are interested, you go to the self-paced PowerPoint and click on that link. So what is a polar molecule? Well, water is a beautiful example of a polar molecule. Polar molecules have electrical charges, and those charges are attracted to each other like magnets. So over here in the picture, what we're seeing is a water molecule, one oxygen, two hydrogens. That oxygen carries a slightly negative charge, while the two hydrogens carry a slightly positive charge, and those positives are going to be attracted to that negative. And you'll see in the next slide, I think, or the next couple of slides, how water molecules are attracted to other water molecules using the same premise of those electrical charges and being attracted to each other like magnets. So hydrogen bonding happens when you take one whole water molecule, so one whole H2O, and you bond it to another water molecule. Within that water molecule, there is this covalent bond. The covalent bond in this picture is shown with the solid line bonding that hydrogen to that oxygen. And again, that's that positive hydrogen being bonded to that negative oxygen. But then you see that we have 1, 2, 3 water molecules bonded to each other. When you bond one water molecule to another water molecule, or down here I guess would be better, you see this dotted line, and this dotted line is a hydrogen bond. It is a strong bond, but it's not as strong as that covalent bond within the water molecule itself. And again, this is hydrogen being attracted to oxygen, the positive molecule being attracted to the negative one, creating that magnetic pull. When we discuss solubility, we're talking about water's ability to dissolve substances when you put them in water. Water is known as a universal solvent because it dissolves more liquids than any other liquid out there. It doesn't dissolve everything by any means, but it definitely dissolves more than any other liquid. What we see down here in this picture is a glass of water, and it is salt being poured into the water. And if we were actually to dump all that salt and take the spoon and mix it up, eventually we get to the point where those crystals of salt will disappear. They have dissolved. So what is the water actually doing to the salt? In this picture right here, we see the little green molecules or atoms, and we see the little purple atoms. The purple atoms are your sodium, and your green ones are the chlorine. If we start up here with the sodium, we notice that sodium carries a slightly positive charge. So when water pulls that NaCl apart, it's going to create these hydration spheres. If you will remember, we did an activity in class with a cut and paste where you had to create these hydration spheres yourself. Na is a slightly positive atom, so when the water molecules create that hydration sphere, it's going to be the oxygen that is attracted to the sodium. The negative is attracted to the positive. It's going to be the opposite with the chlorine. Chlorine carries that slightly negative charge, so it's going to be the hydrogen, that positive hydrogen, that is attracted to that negative charge of the chlorine. And that's how our water molecules get in there and break that salt apart to be able to dissolve it in the water. Surface tension was another topic that we covered. Because water is a polar molecule, it creates this surface tension. And surface tension is nothing but those water molecules sticking together through cohesion that creates that skin, that film on the top of the water. And it allows very light objects like our water bug here to be able to walk on water. When we were in class doing that series of labs, if you recall, we did like a week of labs. This was the lab that we did with the little plastic cups, the water, and the paper clips, trying to get those paper clips to float on the top of the water. Normally, I would take these slides out, but I think this is a great challenge for you to do at home. Whether you're just doing it to refresh your own mind, or I would even challenge you to show this to another sibling or a parent or another adult in your house, not only to show them how to do this experiment, but explain to them, why does the paper clip float and the paper towel doesn't? And explain that concept of surface tension to them. So we saw on the previous slide that surface tension is possible because water is cohesive. That cohesion creates the surface tension. All right, well, what is cohesion? Cohesion is water's ability to stick to water. So we take one water molecule and it sticks to another one, and this creates things like water droplets. So what you're seeing here in the picture is a series of water droplets. So water can stick to itself to create these droplets through cohesion, water sticking to water. The water droplets are actually sticking to silk fibers of a spider web, and it is through adhesion that this water droplet can stick to that thread. So cohesion is water sticking to water. Adhesion is water sticking to something else. So water droplets, cohesion. The water droplets sticking to the spider web, adhesion. We're not going to spend very much time here. A lot of this was covered in the PowerPoint from last week, and we have been touching on this almost in a little bit of every unit that we've done. So for water specifically, the freezing point is 0 degrees Celsius or 32 degrees Fahrenheit. That means this is the temperature at which phase change is going to happen. So if we put water in a freezer and it cools off to 0 degrees Celsius, we're going to see it start to freeze. Adversely, on the other end, the boiling point for water is 100 degrees Celsius or 212 Fahrenheit. So if we add heat to our water and we get it to this temperature of 100 degrees Celsius, it's going to start boiling, and then those water molecules are going to start creating water vapor. It's going to change to a gas. Density for water specifically. Well, most liquids, when they freeze, they become more dense. So when we remove heat, we're creating a higher density in most liquids, which would cause them to sink if we put them in another liquid like water. However, water itself is an exception to that rule. As water freezes and becomes ice, it becomes less dense and it starts to expand, which is what allows ice to float. So if we're looking at this picture here, this is what water molecules look like in liquid form. So if you're staring at your water bottle or a glass of water or water in a pot without any heat on it, this is what the molecules look like. But as we start to remove heat, we start to cool that water off and freeze it, they align themselves in this crystalline structure. Begins to look like this. And so rather than these spaces in between molecules getting smaller and more compact, it's actually expanding. You can see there's quite a bit of room in between each molecule. And this is what gives ice its ability to float. And why would we want it to float? In particular, let's start with this picture down here at the bottom. What you're seeing is a bottom-up picture. We're looking at it from beneath. There's a person up here who's drilled a hole in ice and seems to be participating in some ice fishing. I've done that before, really cold, but a lot of fun. However, if water acted like other liquids in terms of its density, things like ice fishing wouldn't be possible, because as soon as the water starts to freeze, it would freeze not just at the top, it would freeze all the way through down to the bottom. And it would kill all the life living in that water. But because water follows different density rules because of the structure it takes on, you're only seeing a couple inches at the top freeze over. That way, life that's living underneath can still carry on as normal. What you're seeing here is ice floating in iced tea. In this picture, we're seeing an iceberg, and oftentimes what you're seeing floating on top of the water is the smaller piece, while what's underneath is much bigger. But it is floating, and this is massive pieces of ice. And if it were any other liquid, those massive pieces would sink. But because of water's density, they float. Last topic we're going to cover today is the specific heat capacity. Specific heat capacity is a liquid's ability to take on heat and then hold on to that heat for a long period of time. And water happens to have one of the highest specific heat capacities of all liquids, which means it takes a long time to heat it up. But once you've heated it up and it's captured all that heat, it's going to hang on to that heat for a really long time. And so a great example to try and help you understand is a swimming pool. At the beginning of the swimming season, so around now, pools are opening up, and you'll notice that water is still kind of cold. The pool water hasn't been exposed to the sun long enough to be heated up and actually trap heat to keep the heat or the water warm. But as the summer goes on and that water is left to be exposed to the sun, it's going to capture that heat, and then it's going to keep that heat, and the water will stay warm. What happens at night when the temperature goes down? Well, that water's always already captured the heat. So that water, while it might cool a couple degrees, is still going to hang on to all that heat and stay relatively warm. It's also why when you boil water on the stove and then you boil your noodles or whatever you're making, and then if you were to let that pot sit and just turn the heat off and let that pot sit for a couple of hours, you'll find that when you go back to it, the water's, while it may not be boiling, scalding hot, and it won't burn you, that water is still going to be pretty warm. What does that mean for our climate and our atmosphere? Why do we care about this? Well, specific heat capacity affects climate. When we were actively learning this unit earlier in the year, we learned using the example of Virginia Beach or any coastal beach area. When the summer is over and we move into the fall and the winter and the temperatures start to drop, people who live in coastal climates, their temperatures usually tend to stay warmer than those who are further inland. And that has to do with specific heat capacity. All summer long, that ocean water has been heated up and it's retaining all that heat. It's keeping the heat. And now that the temperatures have dropped, it's hanging on to that heat and it's helping keep the temperatures warmer with those sea breezes. So breezes coming off the water where the water is still warm onto the land, keeping the land heated is going to keep the temperatures a little bit higher. So that's why we can say that water stays warmer longer and it acts like a heater for those people that live on the coast. This is it for this PowerPoint. We covered a lot of information. As always, if you have questions, make sure that you write them down and you show up to our Zooms so that you can ask or be in communication with your teacher to make sure that we're clarifying anything that is confusing that you still have questions about. Also, this is the last PowerPoint for the school year, so yay, you made it. I apologize, I'm outside and there goes an airplane. Until next time.